We're going to talk about response of first order systems. We have input that's going to be x right here, and then output which is y, and this transfer function that's here in the pink box, that is going to relate the input to the output. Or if we just write this as an equation, we have y of s equals k over tau s plus 1 times x of s. So we're going to calculate the analytic solution, and then we'll also simulate in Simulink and MATLAB. Okay, and then we'll go over a couple example problems of this system. Okay, so in the time domain, we first of all start out, we have the same x and y. There's our input, and then our output is our y. And if we, so converting this to the Laplace domain, we just look up in our Laplace tables, the derivative is going to be s times y of s plus y of s equals k times x of s. And then if we just factor that out, we get tau s plus 1 equals k times x of s. And just rearranging that, I'm going to divide this over here and then bring this over to this side. We get this what's called a transfer function. So this is in the Laplace domain. We sometimes call this g of s, just our transfer function between y and x. Okay, so we have a variety of different inputs that can go into that that x variable. This is probably the most common one, which is a step, and the m is just the magnitude of that step. So you know, how big is that step? If it's a step of 2, it would be 2 divided by s, for example. Okay, we have another one, which is a ramp. The a is equal to the slope of that ramp. There's a rectangular pulse as well. Okay, so it's going to start off, go to a height h, and then come back down to 0 when it's done, and it'll start at time equals 0. The way you can break this up, you can break it up into two pieces. You have this piece first, which is just h over s, and that's just a step function of height h. And then you have minus h over s times e to the minus tws. So that's just a negative step function at a value of tw. Okay, so it goes up, and then we have another one which goes down, and when we add those two together, we get something that goes up and then back down. Okay, so that's our rectangular pulse. We also have here a triangular pulse as well. Let me just show that. So we have this u of s, or you could say this is x of s, in this case, the input to our system. And what we have is, okay, so we have something that's going to go up and then down and then level out. Okay, so that's a triangular pulse. You know, sine wave, of course, it can be something like that, or an impulse. So right at time 0, it's just going to spike up. It'll actually go to infinity, but if you integrate this signal, then it's going to equal 1. Okay, so the area is going to equal 1, but it goes to infinity. So it's just an impulse, just a sharp spike right at the beginning. Okay, actually the area is going to be equal to a, okay, not 1. If you just had a regular impulse, that would be 1, but we're saying that is a value of a there. Okay, okay, so let's just review a response to a step. Okay, so we have this transfer function, which is y of s over x of s equals g of s. And in this case, maybe this g of s is k over tau s plus 1. Just rearranged, this is what y equals, and then we can plug in whatever we want for this x for the input. So let's say x is just going to be a step, which is magnitude. Again, m is just the magnitude of that step, and then y of s is going to be this signal right here. So if we convert this back into the if we convert it back into the time domain, and we can do that with just looking into looking at our Laplace tables. So let me go to the Laplace tables. I'm going to go ahead and exit out of this, and what we'll do is just go look up something that looks similar to this in the Laplace tables. Okay, so if I come over to my Laplace tables, you can find these in various books. In this one, in the Process Dynamics and Control, it's going to be in Table 3.1 on page 42. And if we scroll down, we're going to see something that looks like our function. We'll convert it back into the time domain. So let me go back to our presentation, and you'll see that that is then going to be our solution. Okay, so this is in the Laplace domain. Okay, so this on the left-hand side is in the Laplace domain, and then we convert it back into the time domain with the help of our Laplace table. Okay, so let's look at a response to a ramp, and then what I'll do is simulate both of these in MATLAB as well. So we have response to a ramp. Again, we just have our transfer function here. Now we're gonna multiply by x of s, and then a ramp is just a over s squared. That's a slope of a, and when we have this solution, then we see it here on the right hand side. It's just k times a over s squared times tau s plus 1. Okay, now if we go back to our Laplace tables, let's just see if we can find it there. And we're going to see that it's not going to be in our Laplace tables. Okay, so I'll go ahead and exit out here. So you can look around for it. I don't think you're going to find it in this one. There are some more extensive Laplace tables where you might be able to find this. Okay, so what do we do at this point? We could do partial fractions, and then be able to separate these into two separate pieces, or we can also use something like Simulink and MATLAB to be able to compute the response. Okay, so let me go back to here. We have response to a ramp. We're going to be so if you do the partial fractions and then do the inverse Laplace, you'll come up with this as your solution. So let's open up MATLAB now and just simulate both of these systems. Okay, so what I'll do is when MATLAB opens, I'll show you how to do it in MATLAB, then also in Simulink as well. So there's multiple ways to simulate these systems. We'll go ahead and start off first of all just with a simple example with gain 2 and time constant 3. But what we need to do very first is define a new variable s, which I'm just going to say is equal to a transfer function, variable s. Okay, so this is a Laplace variable in MATLAB. Okay, so it's a continuous time transfer function, and then I just want to come up with my my transfer function here, with gain 2, so that's going to be the k value divided by 3 times s plus 1. Okay, so there's my transfer function, and then if I use the step command, then and put g in there, then I'm going to be able to compute the solution. Okay, so once it comes up with the step response, you can see it goes up to a value of 2. So it's input is just a step at time 0, and it goes to a value of 1. And here's my output response. And you can see at 3 seconds, I'm about 63% of the way there. Now, if I had any delay in there as well, let me just show you that as well. I'll just say g delay is going to be g times e to the minus. Let's give it 5 seconds of delay. Okay, and then let's step that again, and I'll do g and gd on the same plot. Okay, so you can see the transfer function without delay, and then the transfer function response with delay to a step. Okay, so let's do ramp as well. Step will just multiply by 1 over s, and then compute the transfer function solution. Let's do a ramp instead. So we're going to do, let's say g equals g divided by s. So we're going to add one more s to the denominator term, and then I'll do gd equals gd divided by s as well. Okay, and then let me hit the up arrow until I get this this step command. Okay, so this is the response to a step. You can see that the first order system is going to ramp up. So let me just zoom in down here at the bottom. You can see it doesn't immediately start ramping, but it's going to have just a little period of where the input is going to be ramping right along here, but then the output or the response is then either going to be delayed and then start coming up, or start coming up a little bit more gradually than a ramp. Okay, I'll show this in Simulink as well. Okay, so open up Simulink, and then when that opens, a library browser will appear, and we'll be able to compute the response of both of these in Simulink as well. Okay, so I'm going to create a new model with this button. It'll just be a blank work area there, a sheet for me, and I'll go and make this just a little bit bigger. Okay, so what I want to do now is just come up with a transfer function. Okay, and then search here in the transfer function area, and I'll just put in a first order system. Okay, hit the Control plus just to make that a little bit bigger. Okay, so this is going to be my first order system, and let me change the gain to 2 and the time constant to 3. Okay, so there's my first order system, and then if I want to have different inputs, I can come to sources, and I can have a constant, I can do a ramp, whereas my step is right down here. Here's a sine wave, for example. Okay, so let me just give it a step first of all. Okay, so there's going to be a step function, and the final thing that I'll want is just a scope as well. Okay, so let me check for scope there and drag that one over. Okay, and then if I put this in input of a step, and then there's my scope. I'll do one other thing just to combine the input and the output. Okay, so I'm going to look for a mux, and here it is right here. So I'll combine two signals together. Okay, so we're going to delete that one, and so I'll have my output right there. I have to right click on this line. Okay, so it's a little bit tricky when you're sometimes those lines are really thin and they're hard to get, but if you just come to it and you right click on it, that was a left click. Okay, right click, and that does not look like it's working for me right now. Okay, there it goes. Right click and drag, and then I'm going to bring this off to the scope, and then when I simulate that, I'm just going to go for 10 seconds into the future, and then when I open it up, then I'm going to see the first order response. Okay, so there is my first order response, the input, and then the output is going to go to a value of 2. So let's say I had let me just replace this step input with something else. Let me go to signal sources, and for example, I'll give it a ramp. Okay, and then simulate that again, and then you can see that okay, it's going to go to a value of 2. Let me simulate that just a little bit further. They're going to be one is going to be a slope of 2, and the other one will be a a slope of, it'll be 1, okay? Okay, so it's going to go to a slope of 2, just a line, and then a slope of 1. So there's my input, and then there's my output right there. Okay, so we computed these analytically, but we also did them numerically as well with Simulink and MATLAB. We can put anything we want in there, let's say a sine wave, for example, and then we'll see the scope. Let me readjust this. You can see here, just in Simulink, it just kind of looks a little bit jagged. We may need to go in and change our integration step size. So I'm just going to come in here to some of the options, and let's see, max step size. Let's make that 0.1, just to make a much smoother response there. So these are just some of the issues that you have to deal with when you're numerically integrating these versus analytically. Okay, so you can see our input, okay, and then also our output. The input is going to be in the yellow, and the output is going to be in the purple. Okay, so so that is that's a sine wave as well. Okay, so I'm going to go ahead and close this down. Let's go back to our lecture notes here. Here's the response to the sine wave if you want to analytically compute this. So let me go ahead and just write on this. We have, again, our input is going to be x, and there is that in the Laplace domain. We're going to multiply this and the transfer function together. Okay, we're going to multiply them together to come up with this, and then we'll have to then separate those with partial fractions. So our unknown coefficients are going to be a, b, and c, and then these individual pieces then can be transferred back into the time domain with the help of the Laplace tables. Okay. Or you can go to also to that equation in the book. Okay, let's talk about time delays, because I showed one earlier, but I didn't really explain how to transfer it back into the time domain with time delay. So when you have a time delay in the Laplace domain, it's just this e to the minus theta times s. Okay, so that is, you can take any signal and then just put on a time delay. But to go back to the time domain, all you do is transfer that back as you normally would without the time delay, and then everywhere you see time, you just substitute time minus the time delay, and then also multiply by this step function that goes from 0 to 1. Let's say time equals 0. It's going to go from a value of 0 to a value of 1 at the particular time equals theta. Okay, so there is your step function. So it's going to be 0 beforehand and then 1 after that step. And then you took your original function and just substituted in time minus this time delay. And I'll show you an example of that here. So let's say we had this transfer function or this signal right here. Okay, so that's k times m divided by s divided by tau s plus 1. So just a simple first order system with a step input of magnitude m. And we already went over how to compute the analytic solution to that here. So now if we want to add the time delay, okay, so now we just have this extra time delay here in the Laplace domain, and then when we convert it back into the time domain, anywhere we had time, we just substitute that with time minus theta, and then multiply by this step function that turns on at a value of t equals theta. Okay, so that's all that you do to add time delay, and that's how you can transfer back from the Laplace domain into the time domain with some time delay. Okay, so let's just look at a pumped tank example. So we have maybe a tank car that comes in and periodically fills this tank, and then the reactor here on the right is constantly using this supply. And so we have these transfer pumps right here, and here is a feed pump to the reactor that are controlling the flow rates. Okay, so if we derive just a mass balance, and if we assume constant density, then we have dV dt. The volume is the volumetric flow rate in minus the volumetric flow rate out, and that came from a mass balance with constant density. Okay, so then let's go ahead and just convert this into the Laplace domain, and we have the derivative here, which is just going to be s times h of s, and then we have our inlet flow rate and outlet flow rate, and then we just transfer this into this form where h of s is going to be on the left-hand side of the equation. So we want to come up with two transfer functions. One transfer function that is related to our input. Okay, so here on the top blue box we have h of s divided by qis, and that's going to be just 1 over SA. So we assume that our other input, which was the outlet flow rate, is going to be 0, and then just get the relationship between the h of s and the first inlet. And then to get the other transfer function, we just assume that the other one is 0. All other variables are 0 except those two that you're interested in getting the transfer function for, and that's going to be negative 1 over s, s times a. Okay, so let's okay, so we have our two. Now this is called an integrating process, okay, because there's no steady state gain. It's just going to be 1 over s times a for the transfer function. In this case, a p only controller would work really well. Okay, and then if we had an inlet flow, let's say we had a step input of m divided by s on the inlet flow, then our outlet is going to be m divided by s squared times a, and that's just going to be a ramp. So if you start filling the tank but there's no outlet flow, then the height in the tank is going to ramp up, and that's exactly what we would expect. Okay, so you can apply this to a couple different applications. That was very simplistic. Let's say you had Fukushima Reactor after the earthquake. The water level is designed so that you get coverage of those fuel rods down at the bottom for an extended period of time, but there's indications that hydrogen was given off and the spent nuclear fuel was exposed after 3.5 days. So was there likely a leak caused by the earthquake, or was the level loss due only to vaporization? So we know how much heat is being output from these fuel rods, and so we can compute the amount that should be boiling off after a number of days, and you can compute with this same these same transfer functions. So we do another mass balance here, okay, and there is going to be no flow rate coming in, and flow rate going out, that might be due to the leak, and minus vaporization as well, and then we could compute that from the heat input to the system from the rods. Okay, so you can do this analysis as well. There's a lot of different systems where you basically just want to write your differential equation, and then you're going to be adjusting the inputs to those. A lot of them are going to be first order systems, okay, like we talked about today. I want to cover another example application, which is a distillation stage. This is part of the homework for the process control course. This distillation stage, if we, this is part of a larger column with multiple stages going up and down the column. This is just one of the intermediate ones. And we have, in this system, we have liquid flowing in and liquid flowing out, vapor coming in through the bottom as it travels up, it bubbles up through this, the liquid is coming down. And we're going to assume that the Y1, okay, so this is the vapor fraction leaving the distillation stage, is going to be related to the liquid composition leaving the stage as well. They're going to be at equilibrium. Okay, so there's our relationship between those two. We also have this height that can either go up or down depending on how many moles are going in from the vapor and the liquid. Okay, and then so this is a this is going to be from a mass balance, and then we also have a species balance right here. So this one is relating the the hold up times the mole fraction of the liquid. That's going to be the majority of the moles in the hold up, and then we have our inlet and another inlet right here, the liquid and vapor inlets, and then we also have the liquid outlet and the vapor outlet. Okay, so that's just a species balance for this this system. Okay, so what we want to do is try to find 4 transfer functions. The 4 transfer functions relate this variable right here, so that's x1, and the Laplace domain has to be x1 of s, related to, if we have a change in the inlet liquid mole fraction. So that would be a transfer function that would relate the outlet liquid mole fraction to the inlet liquid mole fraction. This one would be the outlet liquid mole fraction to the inlet vapor, and then we have the outlet vapor to the inlet liquid, and the outlet vapor to the inlet vapor. Okay, so we want these 4 transfer functions, and we're going to use these equations here to help us derive those. Okay, and in this case, the H is the molar holdup, and then the L and the V are the molar flow rates, and then as I mentioned, the Y's and the X's are the mole fractions in the vapor and liquid phase. So Y is for vapor, X is for the liquid. Okay, so there's a couple assumptions that we can make. At the molar holdup, we can say that's going to be constant. Okay, maybe through a weir or something like that that controls the level in each tray. We could say that that's approximately going to be equal to 0, the derivative of that. And then from that, we can also assume that we have constant molal overflow. So the moles of liquid coming in equals the moles of liquid going out. And that would result if you had about equal heats of vaporization between the species that were involved, so that even if you do have some of the one compound condensing, the other compound, the lighter one, is going to be vaporizing, and so you get a constant overall molar flow rates going in and out for the vapor and liquid. Okay, and then also from these 2 assumptions, that means that we can use L and V only. We can drop some of the subscripts that you saw, the L1 and the V2, L1, V1 right there. We can just drop those, and just because this is going to equal L and that is just going to equal V. Okay, so let's go on then. So let's go ahead and work through this. I encourage you to try this on your own, but if you can use this video if you're getting stuck with this problem. Okay, so the first thing that we need to do is linearize and put into deviation variable form, so we can transfer into the Laplace domain with 0 initial conditions, and there'll be linear terms as well. Okay, so let's go through this. We've got let me go ahead and linearize the right hand side of this. So remember, the linearization is f of x and y equals f of x bar and y bar, those are the steady state conditions, plus df dx. I'll plug in x equals x bar, y equals y bar, and then have x minus x bar. And then if I have any other terms like y, z, other variables, I would just take the derivative with respect to those as well, and then continue down. Okay, but those are the only two. I'll have let's see, 4 variables in this case. So let's go ahead and take some derivatives. You're going to see this one's going to be pretty easy because it's already linear. Okay, so I have my 4 variables. I have x1, x0, and then I have y1 and y2. So those are going to be the 4 that I want to linearize with respect to. Okay, so that's going to be the derivative with respect to x1 is going to be negative L times x1 minus x1 bar. Okay, and then let's go ahead and do x0. So that's going to be plus L times x0 minus x0 bar. And let's do y1, and that's going to be minus v times y1 minus y1 bar. And finally, we'll do y2 as well. Okay, so that's plus v times y2 minus y2 bar. Okay, so we have our linearized expression. All that this really helped us do was just to put it into deviation variable form. So as I've linearized this, it just means that I can add this prime, not to those. Let me add them to the x0, y2, x1, and y1. Okay, so there are, as x1 prime, for example, x0 prime, y1 prime, and y2 prime. Okay, and then let me linearize this one on the bottom. So I have y1. And I'll just put all of this onto one side of the equation. So I'm going to have a0 plus a1 times x1 plus a2 times x1 squared plus a3 times x1 cubed minus y. Okay, y1. So I only have 2 variables in this one, but let me go ahead and linearize in this case as well. Okay, so that's going to be, okay, I'm going to take the derivative with respect to x1. a1 plus 2a2 x1. I'll put the bar over that. And then plus 3 times a3 x1 squared. Okay, and then I'll multiply by x1 minus x1 bar. Okay, I'm just going to call this, let me call this one beta right there. That's just going to be a value, a number. And then I'll also add, and then we have negative 1 times at y1 minus y1 bar. Okay, so we have a relationship between y1 prime, which is the deviation variable there on the right, and then equals to beta times x1 prime. Okay, with the beta being this value right there. Okay, so there's one relationship. If I convert that into the Laplace domain, that's just y1 s. I drop the prime when I convert it into the Laplace domain, and that's x1 of s times beta. Okay, so I have one relationship between y1 and x1, and then I have this other relationship up top here, which is my differential equation. So let me now just go ahead and with h constant, that can come out front. And so then I'm going to have now this dx1 dt. That one, if I just plug in the x1 prime equals x1 minus x1 bar, that's just the definition of a deviation variable. If I take the derivative of both sides, this one's constant, so the derivative of that is going to be equal to 0. So dx1 prime dt equals dx1 over dx1 dt. Okay, so I can just substitute that in and put that in deviation variable form as well. Okay, so let's go ahead and just take the Laplace transform of this one. Okay, so I have h s x1 of s equals, and then I have negative L times x1 of s plus L times x0 of s minus v times y1 of s minus v times y2 of s. Okay, so wow, okay, so this is a kind of a big equation, but I'm going to use this one right here, and then also the one that I computed from the other one to then get all of these transfer functions. Let's just go and do the first one, which is x1 to x naught. Okay, now I want all of them to be 0 that are independent, but this I know that y1 is also dependent on x1. So let me go and just substitute that one in there for the y1. So I have s h x1 of s equals minus L x1 of s plus L times x naught of s minus v times beta x1 of s minus vy2 of s as well. Okay, so I'm going to collect all of my x1 terms onto the left hand side of the equation, and I'll factor those out. So s times h, let's see, plus L plus v times beta. Okay, all of that's going to be multiplied by x1 of s. And then on the right hand side, I just have L times x naught of s minus v times y2 of s. Okay, so to get these transfer functions then, what I'm going to do is just assume that y2 of s, I have no change in the inlet composition of the vapor. Okay, and then just get the relationship between x1 and x naught. Okay, and that will be equal to, okay, L divided by s times h plus L plus v times beta. Okay, and then I can do the same thing for the other one. Just assume there's no change in the inlet composition of the liquid. And then it's going to be basically the same thing, but just negative v and the same denominator there. Okay, now to get the final two, I already have transfer functions for the x1 over x naught. Let me go ahead and get it for the y1. I'm just going to use this expression right up here and plug in for x1 to get the y1 as well. So x1 is y1 divided by beta. Okay, so I'm just going to take these two transfer functions and basically just multiply it by beta. Okay, so that concludes this example on the distillation stage. So let me just review what we covered. We covered a little bit about first order systems and these transfer functions and how they respond to different inputs. Okay, so let me turn off the pen. Okay, so let me come back up here. So we had the first order functions, and we talked about different inputs to those that transfer function, and then we talked about the step. There's the first one. The next one was the ramp. We also simulated those in MATLAB and Simulink, as well as the sine wave as well. We talked a little bit about time delays and how you can just time shift that signal back with that substitution and of t minus theta, and then also the step. And then we went over a couple examples like the pump tank example and then also the distillation stage example as well. Okay, so that concludes this video on first order systems. The next one that we're going to cover is going to be on second order systems.